Hi everyone, today we are going to look at how I implemented Helm charts for Cloud Native Payment Hub on Azure Kubernetes Service or AKS. This platform processed millions of daily transactions, requiring scalable, secure deployments with 99.99% uptime and PCI DSS compliance. My goal was to use Helm charts to deploy Java and Golang microservices, ensuring modularity, zero downtime updates, and seamless CI CD integration with Azure DevOps. We will cover the modular chart structure, rolling updates, CI CD pipelines, security measures, and the results that drove high performance and compliance. This diagram illustrates the high-level architecture of our cloud-native payment hub designed to process millions of transactions daily with 99.99% uptime and PCI DSS compliance. It shows the flow from client applications to backend services, highlighting key components: web, mobile apps, API gateway, AKS hosted microservices, Kafka, and PostgreSQL. Each component is optimized for scalability, security, and real time processing, enabling the system to handle up to 10,000 transactions per second. The entry point is our mobile and web applications used by end users or merchants to initiate payment transactions such as purchases or transfers. These apps communicate over HTTPS, sending requests to the API gateway with JWT or OAuth2 tokens for authentication, ensuring secure client interactions. The apps are designed to be lightweight, relying on the backend for all business logic and data processing. The API gateway serves as the central ingress point, routing requests from clients to the appropriate AKS hosted microservices. It handles load balancing, request throttling, and authentication authorization, validating JWT or two tokens using Azure Entra ID before forwarding request. The gateway also provides API versioning and rate limiting, protecting the backend from overload and ensuring consistent client experiences. The core of the system runs on Azure Kubernetes Service with Kubernetes 1.24, hosting Java and Golang microservices like the payment service and reconciliation service. Microservices are deployed using Helm charts. with auto-scaling node pools to handle traffic spikes up to 10,000 TPS. Istio's mutual TLS secures inter-service communication. Each microservice is stateless, leveraging Kubernetes horizontal pod, auto-scaling, and config maps secrets backed by Azure Key Vault. For configuration and sensitive data, Kafka acts as the event-driven backbone, enabling asynchronous communication between microservices for real-time transaction processing. Microservices publish and subscribe to Kafka topics. For example, the payment service emits transaction events which the reconciliation service consumes for data consistency. Kafka's partitioning and replication ensures high throughput and fault tolerance, critical for processing millions of events with low latency. PostgreSQL serves as a primary relational database for transactional data, storing payment records, user details, and audit logs. It's configured for high availability with read replicas and automated backups integrated with microservices via connection pools for efficient querying. For specific use cases requiring enterprise-grade features, we also integrate with Oracle, but PostgreSQL handles the majority of real-time transaction persistence. When a user initiates a payment via a mobile app, which sends a request to the API gateway, the gateway authenticates and routes it to the payment service on AKS. The payment service processes the transaction, publishes an event to Kafka, and persists data to PostgreSQL. Other services like reconciliation consume Kafka events for further processing. This setup achieved 99.99% uptime, processed 10,000 transactions per second, and passed PCI DSS audits with 0 findings. The decoupled design with Kafka and microservices allows independent scaling and rapid iteration, while AKS and Helm streamline deployments. Observability provided by ELK Stack, AppDynamics, and Grafana Prometheus ensures we detect and resolve issues proactively. To make deployments modular and reusable, I created a Helm chart for each microservice, like the payment service with a clean, organized structure. The templates folder held Kubernetes resources like deployment and services, using Helm's templating to dynamically configure settings. Config map stored non-sensitive data like Kafka topic names, while secrets pulled sensitive data like database credentials. From Azure Key Vault using the CSI driver for security. I used environment-specific values .yaml files like values prod.yaml to customize replicas or resources for dev, staging, or production. A parent chart managed shared resources like Istio virtual services for traffic routing, with subcharts for individual services, simplifying dependency management. This modularity made it easy to scale and maintain our microservices, setting the stage for zero downtime updates. This diagram illustrates the Helm chart structure for Cloud Native Payment Hub used to deploy microservices on Edge Azure Kubernetes Service AKS with Kubernetes 1.24. It shows the Payment Hub parent chart, its key files, and charts for the payment service and reconciliation service, including templates for config map, secrets, and Istio virtual services. Here we can see the Payment Hub parent chart, which orchestrates the deployment of the entire Payment Hub application. It contains chart.yaml defining metadata and dependencies on subcharts, value.yaml for global configuration, and templates directory for Kubernetes manifest. The values.yaml file in the parent chart defines global configuration values such as replica counts, environment variables, and service endpoints. These values can be overridden by charts or environment-specific configurations, enabling consistent setting across deployments. The templates directory contains Kubernetes manifest, including deployment.yaml and service.yaml for core resources. The config map.yaml for environment settings and secret.yaml for sensitive data like API keys, integrated with Azure Key Vault. It also includes virtual service.yaml, which defines Istio routing rules for microservices, leveraging mutual TLS for secure communication. We have two subcharts, payment service and reconciliation, each with their own values.yaml and templates directory. The payment service subchart includes deployment.yaml for pod configurations and secret.yaml for sensitive data. The reconciliation subchart includes deployment.yaml and virtual service.yaml, tailoring Istio routing for reconciliation tasks. The chart.yaml in the parent chart lists dependencies on the payment, service, and reconciliation subcharts, shown by dashed arrows to each subchart. This hierarchical structure allows modular deployment where the parent chart applies global settings while subcharts manage service-specific configurations. This Helm structure enables consistent, repeatable deployment via our Azure DevOps CI/CD pipeline with Helm charts version for rolling updates and rollbacks. Config maps and secrets ensure environment specific and secure configurations, while Istio virtual services provide fine-grained traffic management, contributing to downtime deployments. This Helm setup reduced deployment times by 30%, streamlined infrastructure management, and ensured PCI DSS compliance. Through secure secret management. The modular design supports independent scaling of microservices, aligning with the payment hub's ability to handle 10,000 transactions per second. To ensure zero downtime deployments, critical for our 99.99% uptime goal. I configured Helm charts for rolling updates. In the deployment template, I set a rolling update strategy with max surge at 25% to spin up new pods before terminating old ones, and max unavailable at 0 to keep all services running. Readiness and liveness probes like HTTP health checks on health endpoints ensured only healthy pods received traffic. Integrated with AKS auto healing. Helm's versioning allowed us to track releases and roll back problematic updates using Helm rollback, minimizing risk. I use the atomic flag during deployments to automatically revert if any resource failed, ensuring safe updates. This approach kept our payment hub running smoothly during updates, but automation was key to scaling it, which brings us to CI/CD. This diagram illustrates the rolling update process for our cloud native payment hub deployed on Azure Kubernetes service with Kubernetes 1.24. It shows the transition from old pods to new pods, leveraging max surge and health probes to ensure zero downtime deployments for microservices like the payment service. The AKS cluster running our microservices indicates the managed Kubernetes environment. Within this cluster, we perform rolling updates to deploy new versions of microservices, ensuring continuous availability for processing up to 10,000 transactions per second. The old pods block shows pods running version 1.0 of a microservice, such as the payment service with two pods, pod A and pod B. Each pod is monitored by health probes, including readiness and liveness probes to confirm they're operational before the update begins. On the right, the new pods represent the new version 1.1 with three pods, pod D, pod E, and pod F, also monitored by health probes. The additional pod reflect the max surge 1 setting, allowing one extra pod to be created during the update to maintain capacity. Here we can see the transition from old to new pods. Kubernetes terminates old pods one by one as new pods pass their health probes. The max unavailable 0 setting ensures no pods are unavailable, guaranteeing zero downtime during the update. Health probes or health probes are critical for reliability. Readiness probes ensure new pods can handle traffic before they're added to the service, which liveness probes detect and restart unhealthy pods. This ensures only healthy pods serve traffic, maintaining the 99.99% uptime required for a payment hub. Here we can see that the old pods are terminated as new pods are added, controlled by the Helm chart updates in our Azure DevOps CI/CD pipeline. For example, pod A is terminated after pod D is ready, followed by pod B as pod E and F come online, respecting the max surge is 1 limit. The rolling update strategy integrated with Helm and AKS reduced deployment time by 30% and ensured zero downtime updates, critical for PCI DSS compliance and high availability. The process supports our system scalability, handling traffic spikes up to 10,000 TPS while maintaining operational stability. To streamline deployments, I integrated Helm charts into Azure DevOps CI/CD pipelines, automating the entire process from code to production. The pipeline started with building and compiling microservices, pushing Docker images to Azure Container Registry, where Azure Defender scanned for vulnerabilities. After passing unit and integration testing for our GraphQL and gRPC APIs, the pipeline ran Helm upgrade, installed to deploy charts to AKS using environment specific values.yaml files. Terraform scripts updated AKS resources like namespaces or RBAC roles, ensuring infrastructure aligned with application changes. Post deployment, smoke test validated application health and Grafana dashboards monitored metrics like pod status and API latency with alerts for failures. This automation reduced deployment times by 30%, but security was equally critical for our PCI DSS compliance. Here's the CI/CD pipeline for Payment Hub on Azure Kubernetes Service, automating deployments to handle millions of daily transactions. This diagram shows the flow from build to validate, orchestrated by Azure DevOps with Azure Container Registry and AKS as key players. The pipeline starts with a build stage where Azure DevOps compiles Java and Golang microservices and pushes Docker images to Azure Container Registry or ACR. Next, the scan stage uses Azure Defender to check images for vulnerabilities in ACR, ensuring security for our PCI DSS compliance. In the test stage, we ran unit and integration tests for GraphQL and gRPC APIs to catch issues early. The deploy stage uses Helm charts to roll out updates to AKS, pulling secure secrets from Key Vault for configuration. Finally, the validate stage runs smoke tests to confirm application health, monitored via Grafana dashboards. Azure DevOps orchestrates the entire flow, triggering each stage, while ACR stores and secures the images, and AKS is where microservice run live. This pipeline cut deployment times by 30%, enabled zero downtime updates, and helped us maintain 99.99% uptime for 10,000 transactions per second. It also streamlined PCI DSS compliance with automated security checks and monitoring. Now let's look at how we secured this stack with observability tools to ensure reliability and compliance. Security was paramount for PCI DSS compliance. I integrated Azure Key Vault for sensitive data, enforced CIS compliant port security policies, and used Istio's mutual TLS to encrypt inter-service communication. For observability, I configured Prometheus to collect metrics displayed on Grafana dashboards, tracking deployment success and system health. Like Kafka consumer lag, ELK stack logged events for audits, and Azure monitors sent alerts to Slack and email. The results were significant. Helm charts enabled 30% faster deployments and zero downtime updates supporting 10,000 transactions per second. We maintain 99.99% uptime and passed PCI DSS audits with no findings over 2 years, ensuring trust and scalability. Collaboration with DevOps and security teams plus runbook documentation made this a success. This diagram illustrates a security and observability stack for our cloud native payment hub deployed on the Azure Kubernetes service to ensure PCI DSS compliance and operational resilience. It highlights the key components: Azure Key Vault, Istio, Grafana, ELK stack integrated with the AKS cluster, and a PCI DSS compliance reflecting our audit success. The AKS cluster running Kubernetes 1.24 hosts our Java and Golang microservices such as the payment service and the service as the foundation for our security and observability tools. It's hardened with CIS benchmarks and pod security policies, providing a secure environment for processing millions of transactions daily. Azure Key Vault manages sensitive data such as API keys and database credentials used by microservice via Helm chart secrets. It integrates with AKS through managed identities, ensuring secure access without exposing credentials, a critical requirement for PCI DSS compliance. Istio enforces mutual TLS for enforced communication between microservices, protecting data in transit within the AKS cluster. It also provides traffic management and policy enforcement with virtual services defining routing rules, enhancing security and reliability for transaction processing. Grafana paired with Prometheus delivers real-time metrics for the AKS cluster and microservices such as the CPU usage, latency, and pod health. Custom dashboards and alerts notify us of issues like latency spikes or pod failures, enabling proactive resolution to maintain 99.99% uptime. ELK stack, the Elastic, Logstash, and Kibana provides centralized logging to microservices, capturing transaction logs and system events. It allows us to query millions of logs for troubleshooting and audit trails, supporting PCI DSS requirements for log retention and analysis. The PCI DSS compliance badge signifies our system's adherence to strict security standards for protecting cardholder data, achieved through Key Vault secure secret management, Istio's encryption, and comprehensive logging and monitoring. We passed audits with zero findings. These components work together. Key Vault secures secrets, Istio encrypts traffic, ELK logs events, and Grafana monitors performance, all within the AKS cluster. This stack ensures robust security and observability, supporting 10,000 transactions per second, rapid issue resolution, and PCI DSS compliance, critical for our payment hub.